For chapter 16, we're going to look at the basics of working with acids and bases. And this will be continued in chapter 17 when we look at some more elaborate versions once we start making buffers and titrations, as well as some stuff with making solids. But for now, we're just going to start with working with pH, pOH, identifying a strong acid and a weak acid, strong base, weak base, and then how to calculate concentrations of the relevant ions, specifically the hydroxide ion and the hydronium ion. So to start, let's calculate the pH of a solution with a hydroxide ion concentration of 1.4 times 10 to the minus 4. So there are two ways to solve this problem. I'll show you one that I'm going to work through, and then I'll point out the other in case you prefer a different strategy, but the way I show is fine, and I don't mind which one you work with. So for this, what I'm going to do is I'm going to start by finding the pOH of this solution. The reason for this is that pH and pOH are directly related to each other. They have to add to 14, so if I find one, I can find the other. And remember that P, anytime you see a P like this in front of something, it just means to take the negative log of the value of that. Later we'll work with pKa's, so it's just there's a bunch of different things we can take the negative log of. So here, we're going to have the negative log of our hydroxide concentration. So for that, we're going to plug in negative log of 1.4 times 10 to the minus 4. We then find out that our pOH, when we plug that in, is equal to 3.85. Note that you're not done. Don't just circle the answer. You have to answer the question that's actually asked, which is what is the pH, which we can set is equal to 14 minus pOH. So there, we can plug in 14 minus 3.85, and that's going to be equal to 10.15. So you'll notice problems like this should be fairly quick. This would be a reasonable multiple choice question, and you want to be able to identify fairly quickly that, okay, this is the strategy I can use. The other way you could have done this problem is you could use the fact that Kw is equal to H3O plus times the concentration of our hydroxide, our OH minus, and that this is going to be equal to 1.0 times 10 to the minus 14. So you could take your OH minus here, plug it in there, and solve for H3O plus, and then just take the negative log of that number. Now, this strategy I find takes a little bit longer, which is why I did it the way I did, but both work fine. Also, what we're doing here, there's my phone, is that if you actually wanted the H3O plus concentration instead of the pH, I would have recommended using the Kw method. Note that both of these take a somewhat similar amount of time, so do whatever you're most comfortable with. They'll both give you the right answer. Nice thing about chemistry is that as long as you're doing things that are sound, it'll work even if you take a slightly different route to get there. So let's look at a second example. Let's go the other way. We have the pH, and now we want a concentration. So here, we're told that pH is equal to 3.65. Maybe our pH probe told us this. And we instead want to know what's the H3O plus concentration. So now the equation for pH is negative log of H3O plus. Note, if you put H plus as well, that's fine. Books will go back and forth. They're trying to talk about the same thing. So I'm fine if you show the log of H plus or the log of H3O plus. Both work. We'll plug our number in. 3.65 equals the negative log of H3O plus. We'll multiply both sides by negative 1 to get the negative on the other side. We'll have negative 3.65 is equal to the log of H3O plus. Now we have to do the inverse of a logarithm. And since this is a log rather than a natural log, there's no ln here. So there's no e in this one. We're going to raise both of these to the 10. 10 is the power we're going to use, or 10 is the thing we're going to use here to put our powers to. So 10 and log effectively cancel each other. And then we get 10 to the negative 3.65 is equal to 2.24 times 10 to the minus 4. And in this case, because we're getting a hydronium concentration, that's going to be in molar. It's going to be equal to our H3O plus. So this is our actual concentration of H3O plus. Again, a problem that hopefully this will be something when you see you can go through kind of quick. It's just systematic. It's using this equation to do it. It's just recognizing that you can go both directions and how to undo a logarithm. Make sure you can do that. So now let's look at something that is a tiny bit longer, but still in the fairly straightforward camp in the quick type of problem. So here, what is the pH of a 0.150 molar solution of barium hydroxide? So the first thing to identify to know this problem is a little quicker is that barium hydroxide is a strong base. That's important because then you don't have to worry about an ice table. We can assume that it fully breaks down. So that means that if I have a solution of barium hydroxide, it's going to have a one-way arrow. There's not equilibrium. We're not having a back reaction. It's going to turn it into barium 2 plus 2 hydroxides. That part's important. That means that when you dissolve this in water, if we just want the hydroxide concentration, which is what I'm going to want to find my pH, it's going to be equal to 0.300 molar because you have a 2-to-1 ratio. Every time you have one barium hydroxide, it's going to break into 2 hydroxides. So then we can solve this similar to problem 1, where we find the pOH of this, which is the negative log of 0.300. We take that, and we're going to get 0.52. We can then use our equation that pH equals 14 minus pOH, which in this case would be 14 minus 0.52. And that's going to get us a pH of 13.48. So because it was a strong base, this problem was quicker. You want to be able to identify those easily, your strong acids and your strong bases, to help you with solving these problems. So now, let's look at a case where we don't have a strong, but instead a weak, in this case a weak acid. So we're told that we have formic acid, and we want to know what the concentration of H3O plus is going to be for this solution. Note, please don't assume that you have to have a Ka written. I lost my pen on my screen. Where'd it go? Oh, there we go. So this Ka thing here. Note that on the test, you're going to have a table in the back. So you're going to have to know that you should go look up that formic acid is not one of your strong acids. You shouldn't assume that, oh, if I see Ka, that means weak acid. Otherwise, it's a strong acid. That's something you're going to have to be able to recognize when you're taking your exam. So please don't try to use that as an... Assume that if that's not there, it's definitely strong, because that may make you miss something you know how to do otherwise. So here, since it's weak, we want to write out our chemical equation first. So we have formic acid, aqueous, plus water liquid is going to be an equilibrium with, this time the arrow goes both ways since we've got a weak acid, and it's going to make the formate ion plus the hydroxide ion. So here, we're going to do our ice table. So initially, we have 0.200 molar. We're not going to worry about the water. It's a liquid. It's not part of the equilibrium constant. We're going to have no formate ion at the start, and we're going to have approximately no hydroxide. It's important to note that hydroxide is always present in water, so you have a little bit, but we're only going to work with cases in this class where it's so little that it's going to always be treated like it's zero. But do know that there is hydronium there, that it's not that there is actually exactly zero. It's just so much less than this acid produces that it's not going to matter for our problem. But note that that is something we do cover in analytical chemistry, and you want to make sure you recognize that from a conceptual standpoint. There's always going to be some amount of hydronium present if we've got water because of Kw. So since we don't have any formate ion, we definitely have to be losing this. This has got to be minus X. And if we're losing that, that means the others have to be plus X. We'll then go to our equilibrium condition, which is going to be 0.200 minus X, X and X. And our Ka is small enough that I'm going to assume X is small. Note, you can still check this at the end, but I'm going to treat it like the X isn't a big deal. If our Ka were much larger, like it was 1 times 10 to the minus 3, it would be much less likely that X is small, and I would probably have to solve a quadratic. So that means we're going to have our Ka is equal to our CHO2 minus, our formate ion, times our hydronium ion, H3O plus, all over our formic acid concentration. So we're going to plug those in, and that's going to give us that this is equal to, on top, X squared, X times X, divided by 0.200, because we assumed X was small, and that's equal to our Ka, which was given to us in the problem, 1.8 times 10 to the minus 4, although you could look it up if you needed to on a table, if it was on your exam. We're then going to take X squared, and we're going to move our 0.2 over. And when we move our 0.2 over by multiplying both sides by 0.2, we get 3.6 times 10 to the minus 5. We're then going to square root both sides, and we get the X is equal to 6.0 times 10 to the minus 3. And the problem asked us for our H3O plus concentration. So in this case, we go to our ice table, and it's just equal to X. So it's 6.0 times 10 to the minus 3 molar. But note that it doesn't have to ask for something that's just X. So don't just circle your X without paying attention to, is this the answer? It could have asked you, what's your formic acid concentration? And then you have to go and plug back in here. And given in this case, it would just be 0.200 molar because X is small. But you might have to check that in some cases where it's not quite true. Well, let's see. Actually, would it be 0.2? 0.200 minus 6 times 10 to the minus 3. That would actually be 0.194 molar. So in that case, we are okay in the sense that it is less than 5%, so X doesn't change a whole lot, but it does make a small change to it. But the more likely case would be a problem where X wasn't small, and then formic acid changed a whole lot. So you had a different solution where you ended up having a 0.2 molar concentration drop to like 0.17, and that's what we're asking for. So make sure you read your problem and answer the question that's being asked, not the problem just of, oh, I'm used to this, I just circle my X. So let's do one last question in this chapter, and this one will be a little bit longer. We'll have 2 slides to get through this one. We're going to look at the pH of a solution that comes from preparing 525 milligrams of sodium benzoate to 185 milliliters of water. So first I need to identify what's going to be the acid or base in this situation. So we know we have sodium benzoate. I should be able to recognize that this is sodium is going to be commonly present when I have an ionic compound. So it's probably going to be sodium attached to a polyatomic ion, in this case the benzoate ion. That means that it is the benzoate ion that's going to be able to act as a base in this case. Because remember, sodium, Na+, is going to be related to sodium hydroxide, which is a strong base. So Na+ is a conjugate acid that is so weak that it doesn't have any reaction. But the benzoate ion, that's not true for it. So we're going to have to worry about the concentration of our benzoate. So to start, we're going to find out how many moles of benzoate we have, so we can then work with the chemical reaction for that, because we're always going to need a molarity. So we have 525 milligrams, which is equal to 0.525 grams. I just got that by dividing by 1,000. And then we use the molar mass as 144.1 grams for sodium benzoate is equal to 1 mole of our sodium benzoate. And then it's helpful to note, I'm okay if you just recognize, but I like to do this to make sure I know what I'm changing it into, is that 1 mole of sodium benzoate is also, that should be a 5. My H looks really weird. That's an H, I promise. You can hear me talk. Sorry, it looks funny. Is going to give me 1 mole of the benzoate ion. This is why we made such a big deal in 1211 at being able to recognize how polyatomics break apart. So then we get this, and we've got a concentration of, or a number of moles of 3.64 times 10 to the minus 3 moles of our benzoate ion. We then need to get the actual concentration of our benzoate ion. And if we do that, and that's got a minus on it. I almost forgot my minus sign. Remember, because it lost the Na+, so it's got to have a minus to balance that. So we would have 3.64 times 10 to the minus 3 moles. We're going to divide that by our volume, 0.185 liters. And from there, we're going to get 1.97 times 10 to the minus 2 molar. So one thing I note, if I try to actually look up the benzoate ion, you're going to find that you don't see it. But what you do see is the Ka for benzoic acid. So if I want the Kb for the benzoate ion, I can solve that by saying that Kb is equal to Kw over Ka. And so this is equal to 1.0 times 10 to the minus 14 divided by 6.5 times 10 to the minus 5. And this will give me that Kb is equal to 1.54 times 10 to the minus 10. Note that this is not a Ka you should have memorized. You have a K table in the back of your test. You also have one in the chapter 16 slides. I just went and looked at those slides and I got the value from that. It'll also be present on your exam. But you have to know that you can go look for that it won't necessarily say on the problem, Ka of benzoic acid. You have to be able to go look at that in a big table. So from there, we're now going to set up our chemical reaction. Is we have our benzoate ion, and we're adding it to water. And this is going to be in equilibrium with our benzoic acid that we don't have yet, but we're going to form a bit of. And since we're adding a hydrogen ion to this, we've got to remove a hydrogen from the water. So the water is going to become the hydroxide ion. So now we have our initial is 1.97 times 10 to the minus 2 molar. We have not worried about the water. We have none of this and approximately none of this. For our change, we have to lose this because we don't have any of some of the products. We're going to gain these. We're then going to, at equilibrium, have 1.97 times 10 to the minus 2 minus x, x and x. And x can definitely be assumed to be small because look at our Kb, 1.54 times 10 to the minus 10. I'm really confident x is small there, so we're not going to worry about that. So if you want to, if you're going along with this, you might want to take a screenshot of your screen. I'm about to move to another slide. We're going to finish up the rest of the problem. There's not enough work here, but we're going to move on moving our ice table into the Kb equation. So here's our page 2 of our work. So we're going to have that Kb is equal to our benzoic acid concentration. And this time we're going to have OH minus. Remember, because it's a Kb, we have OH minus, not hydroxide there. Divided by our benzoate ion. We're then going to plug our numbers in. And so we have Kb is 1.54 times 10 to the minus 10 is equal to x squared on top divided by 1.97 times 10 to the minus 2. We're then going to multiply both sides by 1.97 times 10 to the minus 2 to get it out of the denominator. And I'm going to have 3.03 times 10 to the minus 12 is equal to x squared. We're then going to square root both sides, so I can get x by itself. And I'm going to get the x is equal to 1.74 times 10 to the minus 6. And we can check that's definitely less than 5% of our starting concentration. From there, since I know that OH minus is equal to 1.74 times 10 to the minus 6 molar, I can plug it in like we did at the very starting question where we asked about POH. So we have, dotted line for my work, POH is equal to the negative log of that number, 1.74 times 10 to the minus 6. We're going to plug that in and get a POH of 5.76. We then get pH is equal to 14 minus 5.76. And so pH is equal to 8.24. Notice that these problems do have a fair amount of work in them, but they are always systematically done exactly the same. This is why it's really important to practice working these different types of questions so you can read one and identify. Is this a weak acid? Is this a strong acid? And then for chapter 17, once we get there, is this a buffer? Is this a titration? Once you identify the problem, this work will be very, very similar each time. But it's important because there's so much of it that you get used to the pattern, or it's going to be very, very hard to get done with these problems in time if every time you have to go through and go, wait, what's the next step in the pattern? Especially for the easier ones, it needs to get really systematic. And that's why I strongly encourage you to practice, not just the problems I'm showing you here, but the problems I recommend out of the textbook, as those will give you practice in doing each of these. And as you see them, you'll get better at being able to identify this is the type of problem I'm doing, and you'll be able to speed up through the work. Also, don't forget to check the fact that x is indeed small. If it were not small, you would have to solve a quadratic formula, just like we did on exam 2. Otherwise, the work doesn't change. It's just when you get to that step right here where you're solving for x squared. Right here. This step here. This step gets a little more complicated math-wise, but is otherwise a similar idea. You're still solving for x. You plug it back in and finish the problem like that. So at most, you'll probably do one of those during the exam because they take so long, but make sure you're still checking that step. And hopefully with that, that'll help you get through the beginnings of acids and bases. In the next chapter, we'll be following up with a more extensive coverage of what can you do that's a little more complicated when you make buffers and when you look at titrations.